So what we have here are two different polynomials, p1 and p2, and they have been expressed in factored form. And you can also see their graphs. This is the graph of y is equal to p1 of x in blue, and the graph of y is equal to p2x in white. What we're going to do in this video is continue our study of zeros, but we're going to look at a special case when something interesting happens with the zeros. So let's just first look at p1's zeros. So I'll set up a little table here because it'll be useful. So the first column, let's just make it the zeros, the x values at which our polynomial is equal to 0, and that's pretty easy to figure out from factored form. When x is equal to 1, the whole thing's going to be equal to 0 because 0 times anything is 0. When x is equal to 2 by the same argument, and when x is equal to 3. And we could see it here on the graph. When x equals 1, the graph of y is equal to p1 intersects the x-axis. It does it again at the next 0, x equals 2, and at the next 0, x equals 3. We can also see the property that between consecutive zeros, our function, our polynomial, maintains the same sign. So between these first two, or actually before this first 0, it's negative. Then between these first two, it's positive. Then the next two, it's negative. And then after that, it is positive. Now what about p2? Well, p2 is interesting because if you were to multiply this out, it would have the same degree as p1. In either case, you would have an x to the third term. You would have a third degree polynomial. But how many zeros, how many distinct, unique zeros does p2 have? Pause this video and think about that. Well, let's just list them out. So our zeros, well, once again, if x equals 1, this whole expression is going to be equal to 0. So we have 0 at x equals 1. And we can see that our white graph also intersects the x-axis at x equals 1. And then if x is equal to 3, this whole thing is going to be equal to 0. And we can see that it intersects the x-axis at x equals 3. And then notice this next part of the expression would say, oh, well, we have a 0 at x equals 3. Oh, but we already said that. So we actually have two zeros for a third degree polynomial. So something very interesting is happening. In some ways, you could say that, hey, it's trying to reinforce that we have a 0 at x minus 3. And this notion of having multiple parts of our factored form that would all point to the same 0, that is the idea of multiplicity. So let me write this word down. So multiplicity. Multiplicity. I'll write it out there, and I will write it over here. Multiplicity. And so for each of these zeros, we have a multiplicity of 1. They're only deduced one time when you look at it at factored form. Only one of the factors points to each of those zeros. So they all have a multiplicity of 1. For p2, the first 0 has a multiple of 1. Only one of the expressions points to a 0 of 1, or would become 0 if x would be equal to 1. But notice, out of our factors, when we have it in factored form, out of our factored expressions, or our expression factors, I should say, two of them become 0 when x is equal to 3. This one and this one are going to become 0. And so here we have a multiplicity of 2. And I encourage you to pause this video again and look at the behavior of graphs. And see if you can see a difference between the behavior of the graph when we have a multiplicity of 1 versus when we have a multiplicity of 2. All right, now let's look through it together. We can look at P1, where all of the zeros have a multiplicity of 1. And you can see every time we have a 0, we are crossing the x-axis. Not only are we intersecting it, but we are crossing it. We're crossing the x-axis there. We're crossing it again, and we're crossing it again. So at all of these, we have a sign change around that 0. But what happens here? Well, on the first 0 that has a multiplicity of 1, that only makes one of the factors equal 0, we have a sign change, just like we saw with P1. But what happens at x equals 3, where we have a multiplicity of 2? Well, there we intersect the x-axis still. P of 3 is 0, but notice we don't have a sign change. We were positive before, and we are positive after. We touch the x-axis right there, but then we go back up. And the general idea, and I encourage you to test this out and think about why this is true, is that if you have an odd multiplicity, and let me write this down, if the multiplicity is odd, So if it's 1, 3, 5, 7, etc., then you're going to have a sign change. Sign change. While if it is even, as the case of 2 or 4 or 6, you're going to have no sign change. No sign change. One way to think about it, in an example where you have a multiplicity of 2, so let's just use this 0 here where x is equal to 3. When x is less than 3, both of these are going to be negative, and a negative times a negative is a positive. And when x is greater than 3, both of them are going to be positive. And so in either case, you have a positive. So notice, you saw no sign change. Another thing to appreciate is thinking about the number of zeros relative to the degree of the polynomial. And what you see is that the number of zeros is at most equal to the degree of the polynomial. So it is going to be less than or equal to the degree of the polynomial. And why is that the case? Well, all your zeros might have a multiplicity of 1, in which case the number of zeros is going to be equal to the degree of the polynomial. But if you have a zero that has a higher than 1 multiplicity, well, then you're going to have fewer distinct zeros. Another way to think about it is if you were to add all the multiplicities, that is going to be equal to the degree of your polynomial.